Hello everyone, my name is Venkatesh Krishnamurthy. I am a third year PhD student in the Department of Materials Science and Engineering at Carnegie Mellon. I will be presenting my work on phase transformation mechanisms in lithium-CFx batteries. We are studying the lithium-CFx battery chemistry from the context of batteries for electric aviation. The key challenge to the successful electrification of aviation is the low specific energy of batteries. Bills et al. Analyzed the performance metrics required of batteries to enable electric aviation and concluded that battery packs possessing a specific energy exceeding 500 watt-hours per kg could enable electric aviation. However, the specific energy of battery packs using an NMC cathode and a lithium metal anode falls short of what is required for electric aviation. This shortfall exists even when using the next generation of transition metal oxide cathodes that are currently being explored. Electrification of aviation thus requires beyond transition metal oxide cathodes. One such cathode is the CFX, which possesses a specific capacity of 864 mAh per gram. When paired with a lithium metal anode, the lithium CFX chemistry could enable the electrification of regional and narrow body jets. So what is CFX? CFX is a class of fluorinated carbons with X ranging from 0.5 to 1.33. It is synthesized by passing fluorine gas over graphite heated to about 400 degrees Celsius. The structure of CFX at X equal to 1 is shown here. The carbon atoms are sp3 hybridized, and each carbon atom is bonded to 3 other carbon atoms and to 1 fluorine atom through covalent bonds. The key advantage of the lithium CFX chemistry is that it has a high specific energy of above 800 watt-hours per kg, which is made possible due to the high specific capacity of the cathode. Additionally, it is non-reactive and has a very low self-discharge. However, its biggest disadvantage is that it is not rechargeable. In order to understand why, we investigate the discharge mechanism. Watanabe and Fukuda proposed that LiF and graphite form during discharge. This discharge mechanism was supported by evidence of LiF crystals in the discharge product. Stanley Whitcomb proposed that lithium intercalates into CFX during discharge. For LiF to form during discharge through reaction 1, fluorine has to diffuse out of CFX and react with lithium ions coming from the anode to form LiF. For reaction 2 to occur, lithium ions has to diffuse into CFX. Therefore, we can examine the feasibility of the reactions by looking at the activation barrier for fluorine diffusion and for lithium diffusion in CFX. If fluorine has a very low migration barrier, then reaction 1 is favorable. On the other hand, if lithium has a very low migration barrier in CFX, then reaction 2 is much more likely to occur. We use DFT calculations to compute the activation barrier for lithium and fluorine diffusion. We find that the migration barrier for fluorine diffusion is about 2.6 eV, whereas for lithium diffusion, it is just 0.06 eV. Therefore, kinetically, we are more likely to form a lithium intercalated Li-CFx during discharge. So we use DFT calculations to obtain the structure of LiCF, which is the end product, and this is the structure that we obtained. Well, then how does LiCF decompose to form LiF and graphite? We know that LiCF decomposes. There are multiple reports in the literature that investigated the discharge reaction of the lithium CFX chemistry, where they found evidence for the formation of LiF. From our DFT calculations, we estimate the driving force for LiCF to decompose to form LiF and graphite to be about 0.5 eV, which is 20 times kBt at room temperature. How does LiCF decompose to form LiF and graphite? We propose two mechanisms. One is atomic diffusion, the other is cooperative sliding. In this mechanism, the transport of lithium and fluorine ions from LiCF into LiF occurs via vacancy-assisted diffusion. The diffusion of atoms at the surface of LiF slab is expected to be low in energy. I am currently running the DFT calculations to compute both the vacancy formation energy as well as the activation energy for the diffusion of lithium as well as fluorine. The migration of lithium ions in LiCF is shown in this animation. The second mechanism is cooperative sliding. In this mechanism, the LiF slab in the LiCF slides cooperatively to form LiF crystals. There would be a rearrangement of the lithium and fluorine atoms here, which I have not shown. So after the slabs slide in LiCF, we are then left with these graphene layers, which then come together to form graphite. We hypothesized that this mechanism could occur with a very low barrier, as the LiF slab is not chemically bonded to the carbon layer. As hypothesized, the energy barrier to cooperative sliding was found to be about 0.003 eV per lithium. However, it must be noted that this barrier scales with the size of the AB plane. Therefore, it is expected to occur only in small crystals. But then how small is small? We then built a simple model to estimate the size of the LiCF grain in which this mechanism could occur. So the LiCF grain, we are assuming that the LiCF grain is composed of Na units and Nb units along the A and the B axis respectively. We also define the following terms. Ba is defined as the barrier to slide LiF slab in 1 unit of LiCF, which was calculated to be about 0.003 EV per lithium. N is the number of LiCF units in 1 unit cell of LiCF, and delta Gn is the free energy change per lithium for forming LiF and graphite from LiCF. So assuming that the LiF slab slides along the A direction, the delta G per unit of A that is slid is equal to N times the delta G, which is the, so this is the total free energy change inside 1 unit cell times the number of unit cells which is slid, which is NB. We are sliding along A, so there are NB units of LiCF that slide. Now the barrier to sliding, it scales with the size of the AB plane, in which case it is Na times Nb times the barrier per unit cell. So we expect that this LiCF to decompose via this mechanism when the free energy change upon sliding is comparable to the barrier. So if we assume that these are equal, then we get the size of the AB plane to be about 42 nanometers. So if the size of the LiCF grain is less than 40 nanometers or so, then we expect that sliding would happen with very little barrier. So in conclusion, an alternative pathway for the formation of LiF is explained. Rather than forming LiF directly upon discharge, lithium intercalates into CFX to form an intermediate phase, which is LiCF, and this LiCF phase subsequently undergoes decomposition to form LiF. We also have proposed 2 mechanisms by which the LiCF could decompose. And also we expect the cooperative sliding mechanism to likely dominate in small grains. I'd like to thank my advisor, Dr. Venkatasubramanian Vishwanathan, as well as members of our research group for their useful inputs and wonderful discussions that we have had in this project. I'd also like to thank the Pennsylvania Infrastructure Technology Alliance for funding this project. The computational portion of this work was carried out in our Arjuna cluster, which is funded through the College of Engineering at Carnegie Mellon. Thank you.